today's class we'll be talking about a differential drive car. Okay, so what is a differential drive car? I'll draw a schematic and then we can start trying to model a differential drive car. Okay, so that's basically the chassis of the car on which you'll mount electronics and the wheels and so on. And what I'm going to do is just going to draw an axis. Say this way. Yeah, I'll put the wheels. This is a top view. So let's say those are the wheels as seen from top. Now well, let me write that down. Wheels. And each of these wheel is motorized. That means that each wheel is connected to a separate motor. So because it's connected to a separate motor, you can spin the wheels with whatever speed you want them to spin. And now if you really make a car like this, like a circle, and you put wheels, it's very likely that it'll tip forward or back depending on the mass of the chassis. So what is done is they actually put a caster somewhere so that it's like a 3-point support, not just 2-point support. Like, it's difficult to make something balanced on just two legs or two wheels. So there is a caster somewhere, let's say here. You know what a caster is? If you see some of these rolling chairs, there is a wheel which makes and enables the chair to move in any direction you move it. So an example would be if you went to a big box store where they had those carts, you'll see that the forward wheel is usually a caster. So it can orient in any direction. So if you move it to the left, it'll go the cart will move to the left. If you move to the right, move to the right, and so on. Some of them have casters on all sides. If you go to IKEA, you'll see casters on front and back, which enables it. You can move the cart any way you want. So that way you are not restricted to movement. It's interesting. There's no caster. There's no chair like that in this room. Usually every room has a chair with caster. I could have shown you what a caster is. Okay, just Google search caster wheel, and then you'll see what a caster wheel is. Okay, so for all practical purposes, so that's how you will design it. You'll put wheels, you'll put a caster, so it's balanced. I will not show a caster in my drawings because it just adds more clutter to the figure. But because you have motors on each of those wheels, you can spin those motors. So let's call this, just the way it's drawn, let's call it the right wheel. Let's say phi dot is the rate of change of the speed of the right wheel. So phi dot r and phi dot l, left wheel. So one way of getting this to move is, well, you want this car or differential drive to move straight and turn left or right. If you want it to move straight, all you do is move the right and left wheel at the same speed, and it'll go straight. If you want it to move to the left, clearly you want to spin the right wheel faster than the left wheel. And so you start turning left. So if you want to move straight, you want to set phi dot r, phi dot l to the same value. If you want to turn, set p dot r, p dot l to different values. So question, is your automobile, the one which you drive to, say, campus or pick up your groceries, is that a differential drive car? Is it a differential drive car? Do you have separate motors for the two wheels? You don't. It's not a differential drive car. What you have is what they call Ackermann steering. So you have the engine is powering either the forward, usually it's the forward wheels, but let's assume that it's powering the rear wheels. And then you have a steering, which basically steers the forward wheels left or right. Okay, that's very different from a differential drive car. Okay, you can either have forward wheel drive or all wheel drive, which will power all, but then you also have the means to steer. So that model is slightly different. So this is not what is in your car, but it's very useful for robotics because it's very easy to build one of these cars. Just put in a motor to each of the wheels and you have a car. Okay, so now let's try to see how we can describe the movement of this car, a differential drive car. Okay, so what I'll do is, this is again one of the applications where what I taught last class and talked about homogeneous matrices will show up. Okay, so another way to apply that. So let's start modeling it. So we want to start the car in some position whose we'll just align it with the world frame. So let's draw the car again. Yeah, that would suffice. Then we go. Yeah, I'll need two of those. Oh, well, it did not quite copy that. Copy. Okay, let's fit in the axis. Okay, this point, okay, remember the wheels are here. Let's describe it well with let's call it C. So its position is xc0, yc0. And note that I've drawn frame 0, which means that that's my global frame. That frame is going to be fixed. And I'm just assuming that when the car starts off, it's basically positioned such that it is oriented with the world frame in frame 0. Okay. A few things for dimensions. There is, let's draw this wheel a little bigger. Okay, so we'll define a radius for the wheel. And then we'll also define the distance between the wheel and this point C. That's point C is actually midway between the two wheels. So this, let's say, it's basically half the width of the car. So let's call it B. Okay, so this is at time t equals 0. Let's say position at t equals 0. Okay, now because you spin the wheels, the car moves around. And question, yeah. It's usually from the middle of the tires to the middle. Yeah, it doesn't really matter, but yeah, it's middle if you want to be very particular about it. It's basically the contact point of assume that the contact point is right in the middle of the wheel. That's what we care about. And so let's say that this car rotates moves, and so it's the new position is shown. I need to draw a new axis. So this is my axis of frame 1. So in the process, it basically has rotated by an angle theta. So I'll show that here. And clearly this point now, the point which was midway, I'll denote that as xc, yc, but in frame 1. So I put 1 as a I raise it to 1, right? So that's the configuration. And we could also put the speed, which will come in the equation. So let's say that the speed of the right wheel is v dot r, left wheel is v dot l. This is position at some time t equals say t1. Okay, what we want to get to is we want to be able to describe the movement of the differential drive car. So essentially, it will be the point xc1, yc1, but we really don't want it in frame 1. We want it in frame 0, because remember that frame 1 is actually moving. As the car moves, frame 1 will move, and really we care about how it's positioned with respect to the world frame. So my goal here is to compute xc, yc. Okay. Now the issue is that there is no, unlike the manipulator we talked about, we could write a formula for the end effector, right? There's a formula, but here it turns out that there is no closed form solution for xc, yc. It's actually a function of the speed. So we can actually end up, I'll show you, we will, or rather derive an expression for xc dot, yc dot in frame 0, or rate of change of the position of c. Then we will integrate this equation or equations to compute xc0, yc0. And then and that's how we'll be doing the animations. Once we have xc0, yc0, all we need to do is, once you have xc0, we just draw a circle around it. That's pretty much how you describe the differential drive car. Okay, so let's see how we can derive an expression for xc dot yc dot. Yes, there are two parts to it. First part is part 1. We're going to derive an expression, assuming that straight if you spin both the motors at the same speed, the differential drive car will move straight. We'll assume that we'll derive an expression for the xc dot yc dot, and then we'll derive another expression for the rate of turning. So in order to derive this part, what we'll do is, if phi dot r is equal to is not equal to 0 and phi dot l is equal to 0, phi dot r being the speed of the right wheel, we'll see that the point this point, the wheel will actually move straight, right? So it'll be, if this is the configuration initially, if just phi dot r is changing, then you'll see that the left wheel will not move, but the right wheel will move by a small amount. So let me just draw this big. Left, right. So phi dot r is changing, and so this point will move. And so what will happen is L will be fixed, and we see that this point, the middle of the point C, which is of interest, has actually moved so much. So since point C is exactly midway, we can actually compute that distance moved by point C by using some simple calculation. So this distance is basically the distance moved by the right wheel. It's going to be the radius times phi dot, right? If phi dot is the speed, then the arc length, so this is the wheel, this is r. If it moves by this is phi, the distance moved when phi dot is changing by constant amount is going to be s equals r phi, right? S being the arc length, and then s dot, which is the velocity, is r phi dot. So that's why this is r phi dot. But we see that point C has only moved half the distance because the two triangles are similar. This triangle is similar to that triangle, and then C is midway. So distance moved by xc, or in this case, since it's a velocity, it's going to be xc dot in frame 1 is going to be r times phi dot divided by 2. Now we can do the same thing the other way. We can assume that phi dot L is not equal to 0, but phi dot R equal to 0. And we'll have exactly the opposite, which is the left wheel will move, right will be fixed. In this case, the distance moved by xc1 would be R times, this should be R, by the way, it be phi R, R times phi dot L divided by 2. Okay, now, because these things are linear in phi, you can say that if both moved, that is, if phi dot L is not equal to 0 and if phi dot R is not equal to 0, then the distance moved by C is going to be the sum of the two. So that's by superposition, phi dot R plus phi dot L. This 1, this is 2, from 1 to by superposition. Okay, now when we have the right wheel moving and the left wheel not moving, the question is, what is the distance moved by point YC? So YC is the Y coordinate. So it will be the distance moved in the Y direction. What will that be? Does it move in the Y direction? Will it move? It will actually be 0. The car cannot move in the Y direction when you have it configured in this fashion. It's just a property of the differential drive car. So yc dot is 0. It's just like a bicycle. A bicycle can go straight. It cannot go to the side. Or a unicycle, whatever you like to call it. So we've got an equation for the movement of point C in frame 1. We want to find the corresponding equation in frame 0, because ultimately what we care about is in world frame. So we can now use some of the things we developed earlier to find that expression. So we wrote down a formula for C0 as R10 C1, where C0 is XC0 YC0, and then C1 is XC1 YC1. Okay, this is not the homogeneous matrix. It's just the translation part of it. So I did not write the homogeneous matrix. We're not really looking at the rotations rate. We're just looking at the translations. So if you want to find the rate of change of C dot, it's going to be R10 C1 dot plus, using the chain rule, R1 dot times C1. Now, since we're only looking at translations, only translation, the rotation part is going to be 0. The rate of change of the rotation part is going to be 0. Translation. So R dot is 0. So we can write, expand this out, x dot c, y dot c 0 equals cosine theta minus sine theta, cosine theta, and this is xc1. Okay, but we know something about x dot c1 and y dot c1. So cosine minus sine theta, cosine theta. So x dot c1 is r divided by 2 v dot r plus v dot l 0. Yeah, and then it's a straightforward thing to multiply those two matrices together. So we can write a formula for xc dot is r divided by 2 v dot r plus v dot l cosine theta, and y dot c0 is r divided by 2 v dot r plus v dot l sine theta. Okay, note that yc dot in frame 1 is 0, but y dot c in frame 0 is not 0. It is whatever is written there down. Okay, so that's the first part. What is, yeah, question? The rotation is not 0. I'm coming to that. Theta, there's a formula for theta or theta dot also. Right now, I'm only considering straight motion. So that's why this is 0. But rotation is not 0 in general. Okay, so that part only gives me what is the position of the robot, but doesn't really tell me what angle it has rotated. In fact, I have something for the angle. It's theta, right? I need to basically find a value for theta. So let's take this again, this figure, and then derive that. Okay, so part 2, effect of rotation due to different speeds. Okay, so now let's look at what will happen if p dot L equals 0 and phi dot R is not equal to 0. Okay, we're just looking at the effect of rotation. We looked at translations, but we're going to look at what's the change of rate of change of the yaw or rotation theta due to this. Okay, the same figure, we have this point, left wheel is 0, right wheel is going to be as it is going to move in an arc. So that will be some theta. Okay, because of these conditions. Now, not phi, but theta. Okay, now I need to find an expression for rate of change of. I'm trying to get a formula for rate of change of theta or the rate of rotation. So for that, what I can do is the following. This distance we know is 2b, right? This green part, the arc length can be obtained two ways. One is you could obtain that because this motor is spinning. So that is simply r times phi dot r. Okay, that's the distance moved by the right wheel because of rotation of the right wheel. But it should also equal to 2b times theta dot, because remember this is a circle of radius 2b, and theta being the angle swept by the circle in that small time that this right wheel is rotated. So we can write a formula for theta dot as r times phi dot r divided by 2b. But this is, remember, the way I've shown it, it is counterclockwise. Counterclock. I could do the same thing for the other way, which is I could keep r fixed and spin the left wheel at a certain speed, and that will cause the differential drive to spin clockwise. So what I'll get is a similar expression, except that it'll have a negative sign. So if you have phi dot r equal to 0 and phi dot L is not equal to 0, then theta dot would be negative r phi dot L divided by 2b. So I can now take these two cases and superimpose because they are all linear functions of phi. So now I can get the general case, which is if phi dot r is not equal to 0 and phi dot L is not equal to 0, then let's use these expressions. Let's call this 3. Let's call this 4. From 3 and 4, theta dot is r divided by 2b phi dot r minus phi dot L. Okay, so that's the rate of change. And so I can write down all the three formulas down. So it was, see, I had star, and let's call this, tilde. So 0.5 v dot r plus v dot l cosine theta sine theta, and this will be 0.5 r divided by b v dot. One way of simplifying this is to define new variables. V equals 0.5 r v dot r plus v dot l. V being the linear speed, it's basically the average of the speeds of the two wheels. And we can define omega as the rotation part of it. So that would be 0.5 r divided by b phi dot r minus phi dot l. So if you know the speeds, you can find v and omega. And now this expression boils down to something which looks like this. Easy to keep it in the head. X dot c, y dot c is v sine theta, and theta dot equals omega. So if you see the equations of a differential drive car, you'll normally see it in this form, where v and omega are given by these expressions. So really simple, v cosine, v sine, and omega. So you can do the same thing for a Ackermann steering, something which is there on your cars, and you'll get a similar expression. Actually, you'll get the same for x and y, but I think the theta dot expression will be slightly different. It will be based on the steering you use in your car. We need to use these equations to create an animation of the robot, right? So how do we do that? Well, for the manipulator, it was simple. You had a formula for the position of the end effector and any point on the robot, and you could just plot that. But here, the problem is we do not have a formula for the point C. We have the formula for xc dot, the rate of change of xc. And so what we can do is we can actually integrate this equation. So the simplest way of doing this is to use, you might have heard of this Euler's method, where you expand this out. So this is known as Euler's method of integration. So given this formula, we just write down the expression for that in terms of calculus. What's x dot c? It's basically xc at time step t plus 1 minus xc at time step t divided by delta t. So I'll use that and expand that out. Xc at time t I plus 1 plus the time step. I'll call that h times v at time t cosine theta at time ti. Same for y. You know something about what is the state of the system at time step t. So beginning with 0, you know something about what is how the configuration is at the time step 0. Then you can compute what happens at after a small time step h, and you can do it at 2h and 3h and 4h, and that's how this equation works. However, you also need to know what v of ti and omega of ti is, and these are your controls. How you change v and omega depends on you. You can change the speed, you can change the angular speed the way you want, and the robot will behave in response to that. Also note that ti plus 1 is h plus ti. That is the increment in the time. So in order for this to work, we need to know xc at t0, yc at t0, and theta at t0. We also need to know or specify what the velocity you're going to impose, and omega you're going to impose as a function of time, and then you can just do this animation. So I'll show you how to do this in Python. Just make an animation. And then once you do that, we can do more interesting things with it. Okay, so let me run this first. This is just the animation of the differential drive car. I chose some radius and just made it draw L. I'll just run through the code and show you how it is done. Essentially, there's a part where you initialize so the main part is here. Okay, so it's like less than 100 lines of code. Anyway, so what I do is I basically wanted to go straight and turn. So clearly I wanted to have a non-zero v, and then I would turn. So I change the v to 0 and then spin it a little bit, and then again go put a non-zero v and keep the omega 0. So I have 3 timestamps here, or 3 times ranges. First time range I just put 1 for the velocity in this case the y direction. Then I keep the velocity 0 and I put the angular speed to be pi divided by 2, or 1.57. And then once it turns, I put the speed back to 1, and that's why it goes straight and down. So once you set this up, how do you really do this? Well, I use the Euler integration, which I wrote about. What Euler integration does is there's a function here which basically takes in v and omega, something which I already set. It takes the initial value, x, y, and theta. So I know what the value is. I set it up at time t equals 0, and I just use the formula x dot c, y dot c, theta dot c in the fashion I wrote down there. X at time step ti plus 1 is x of 0 plus x dot times h, and so on. So once I have that, I have the value at a new time, and I keep doing that. And once that has all been populated in an array, I can then go and plot it. Essentially, I draw the point xc, yc is the center of the circle. So once I have the center, I can draw a circle around it, which is done somewhere. Line. Yeah, so x2, y2 basically, you can see cosine, sine. That basically specifies the circle. You could also do it using a patch. I did not use a patch here, but I just used, I basically drew a circle by connecting short segments to create the circle. And that's pretty much it. So this is how you'll get it to move. And this by itself is not useful. So next class, I'll show you how you can use this idea to draw a curve. Less like for the manipulator, we draw a circle, we'll draw circles and other curves using the same idea as we did for IK. So I'll